Welcome to our Quantum Deep Dive. Today, we're exploring a really fascinating essay by Jörg Owe Schnappat that sits right at the intersection of quantum physics and artificial intelligence. We're going to unpack a technique that could seriously change how AI learns and maybe even solve one of its biggest, most expensive headaches.
You know, it all really starts with a fundamental problem in AI. It is absolutely starving for data. To get smart, it needs to see a massive amount of the world. And for an AI, that means processing tons and tons of high-quality data. Without that rich diet, an AI is basically like a student who's only ever read one book. It just can't handle the real world.
Yeah, exactly. And if it doesn't get enough variety, it starts to do this thing called overfitting. Just imagine you're trying to teach a kid what a dog is, but you only show them pictures of golden retrievers. They'll get fantastic at spotting golden retrievers, but the second you show them a chihuahua, they're lost. That's overfitting. The model just memorizes what it's seen instead of actually learning, so it fails the moment it faces something new. Okay, so here's how we're going to break this down. First, we'll get into the weeds of this data dilemma. Then, we'll look at the old tricks people use and why they're just not cutting it. After that, we'll open up a new quantum toolbox, see how to put it to work, check out some mind-blowing real-world applications, and finally, take a look at the path forward. So, to fight this data scarcity, developers have a trick up their sleeve called data augmentation. The idea is pretty simple. If you can't find more data, just make more. But as we're about to see, the traditional way of doing this has some pretty big limitations. It's kind of like making a photocopy of a photocopy. You get more pages, but the quality doesn't really improve. Right. The classic approach uses these simple rule-based tricks. You take a picture of a cat, you rotate it a little, you flip it, maybe crop it. You're creating more data, sure, but it's all super repetitive. You're not exploring anything truly new. The essay calls this a data echo. You're making the dataset louder, but not necessarily adding anything new to the conversation. And this slide just lays it all out, doesn't it? The core difference is huge. Classical methods are those photocopies with tiny adjustments. But the quantum approach, man, that's like dreaming up entirely new, totally plausible versions of the original. It generates something that is genuinely new information while still respecting the original structure.
All right, let's move into the quantum realm. This is where things get really, really cool. It all comes down to two of the most mind-bending but powerful concepts in all of physics. These are the tools we're going to use to build a completely new kind of data factory. So first up, we have superposition. The best way to get your head around it is to picture a spinning coin. While it's spinning, it's not heads and it's not tails. It's kind of both at the same time. Well, a quantum bit or a qubit does the exact same thing. It can be a 0, a 1, or a rich blend of both, all at once, holding this huge landscape of possibilities. And then there's entanglement, which is, well, it's wild. It's like having two magic gloves in different boxes. The instant you open one and see it's the left glove, you know instantly that the other one is the right, even if it's a million miles away. Their fates are linked. And for data, this is an absolute game changer. It lets us create new data where all the different features have complex built-in relationships, so the new stuff we make actually makes sense. Okay, so we've got this amazing quantum toolbox with superposition and entanglement. How do we actually use it to make more data? Well, it's not like you just plug it in. The secret sauce is a really clever hybrid approach, using the best of both classical and quantum computers together. This process is just so cool. You start with one piece of data, say a single medical scan. You encode its information into a quantum state. Then the quantum computer works its magic, using superposition to explore this whole universe of tiny, plausible variations. Then you measure it, and each time you take a measurement, that cloud of possibilities collapses into one new unique data point. You do it again, you get another different one. It's like pulling unique snowflakes out of a cloud. And this is the absolute key takeaway. We are not just making copies. In fact, there's a fundamental rule in quantum mechanics, the no-cloning theorem, that says you can't perfectly copy an unknown quantum state. So instead of copying, what we're doing is sampling from that rich, probabilistic cloud of possibilities. That's how we get data that's both brand new and structurally sound. Okay, this might all sound a little bit abstract, but trust me, the real-world implications here are just massive. This isn't just a neat trick for scientists. It's a tool that could solve huge problems in some really important industries. So let's bring this down to earth and see where this could be a game changer. Take medicine, for instance. High-quality data is super scarce, and obviously patient privacy is everything. This is a total game changer. Imagine having just a handful of scans for a really rare disease. With this, you could generate thousands of synthetic but totally realistic variations to train an AI. That AI could then learn to spot the disease far more accurately, all without ever compromising the original patient's privacy. Or how about finance? The biggest risks are those super rare black swan events, like a sudden market crash. By definition, they almost never happen, so you don't have data to train your models on. Quantum augmentation lets you create realistic simulations of these disasters, which means you can build financial systems and critical infrastructure that are way more resilient when the unexpected actually happens. And in cybersecurity, this is where it gets kind of wild. You could use this to literally dream up new types of cyber attacks that no one's even thought of yet. By exploring all the ways a system could be attacked, you can build defenses for threats that don't even exist. It's like building a shield for a sword that hasn't even been invented yet. So this is all incredibly exciting stuff, but we have to be realistic here. This isn't something you can just download tomorrow. As with any revolutionary tech, the path forward has its share of challenges and hurdles we still need to clear. Right now, we're living in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, you can think of today's quantum computers as these incredibly powerful, but also incredibly finicky Formula One engines. The slightest vibration, what physicists call noise, can throw the whole thing off. So the biggest challenge is figuring out how to separate the useful quantum randomness we want from all that useless hardware noise that just causes errors. But the good news is progress is happening fast. I mean, right now, anyone can go online and start experimenting with this stuff on cloud platforms. In the near future, we'll get better at correcting for errors, making it reliable for high-stakes industries. And then, further down the line, we get to the era of fault-tolerant quantum computers. That's the point where this becomes a standard tool in every single AI developer's toolkit. And that really brings us back to the core vision from York Oeschnepet's essay. The end goal here is to fundamentally upgrade AI's ability to learn. It's not just about giving it more data, it's about giving it a much richer, more diverse diet of data, the kind that truly prepares it for the messy, unpredictable real world. So this leaves us with one last big thought to chew on. For decades, the biggest thing holding AI back has been the data bottleneck. So what happens if that bottleneck just vanishes? If we could generate perfect, limitless data whenever we needed it, what becomes possible? What are the truly world-changing problems in science, medicine, or society that we could finally solve? We want to say a huge thank you to Jorg O. Schnepet for the incredible essay that inspired today's explainer. To learn more and dive deeper into the original research, be sure to visit schnepet.de. Thanks so much for watching, and goodbye.
Schnepet.de is a private project by Jorg O. Schnepet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.